Nice to see you on this rainy day. Our thanks to Update, who was able to run the camera today. Sasha had some conflict, so he'll be back this afternoon. So, I usually begin with the review, as you know. And I hope that's the way you also study mathematics, is by making reviews each day, various subjects. It really helps. So we start with the G action. As you've seen, that's sort of the fundamental thing that I'd like to talk about on X, which is of course some set. And one of the first things you look at is the orbits in X. If you're thinking of symmetry, these are the things that you want to really identify. The points are all the same from the point of view of the symmetry. And the notation is G, and I like to make a little point X. Let's write down what they are instead of all possible things you get by applying the group. Very simple thing. And then we have an idea. And the idea is to introduce an equivalence relation. Equivalence, what I just mentioned. So, well, Mr. Pham is not here this morning, but he said it last time, X is equivalent to Y, even only the orbits are the same. This kind of thing is used throughout mathematics, so there's nothing new here, really. And one should notice this is the same thing as if and only if there exists an element in the group with, which pushes X over to Y or vice versa. Because it's a group, the axioms are free of charge. The inverse is there and so on. And you learn from, well, some of you from my analysis course in basic mathematics, that when you have an equivalence relation, I like to write it vertically for some reason. You go to X modulo equivalence. And I always like to draw a picture of X, and here's a picture of the equivalence class, space of equivalence classes. And an element down here is the equivalence class of X, that's the entire thing. But I like to draw it up here. This is the set of, here X is in this equivalence class, and this is the set of X, Y, such that X is equivalent to Y. And I always draw optimistic pictures, as you know. This is a very optimistic picture, but maybe some of the equivalence classes are finite, maybe they're very, very big, who knows. But it's the way the picture looks. Now, in this case, then, of course, the picture is these things upstairs. In our case, so I call this the upstairs space. This is downstairs. In our case, upstairs, let me just write again, the equivalence classes are the orbits. The equivalence class of X is the orbit, and that's just the way it looks, right? I mean, orbits, and many interesting things. So I thought, since this is a little bit abstract, we should look at a concrete example before we're doing anything more. So let's look at our favorite example, my favorite example so far. A simple example. It's not so simple, actually, when you start looking at it, of the square. Square, and of course, inside the right. I just introduced your equivalence relation that you talked about last time, because you told me the equivalence classes were the orbits. You're right. So let's talk about the square. It's so simple that it's complicated. So let's remember, well, let's draw a picture of the square, a little bit bigger this time so it's easier to look at. Look at the square. Yes. Has the corner points and so on. And we found out that the symmetry group, so G in this case, is the symmetry group of the square, which we talked about at great length, motivating many things. We computed this thing. This is the dihedral group consisting of 8 elements. I think maybe there's not, I think I only have one bar diagram. Dihedral groups consisting of 8 elements. And I would like to write all of its elements. With 8 elements I can write. It's not so hard. Well, the first thing you write is identity. I like to write it as 1. Then there are rotations. I like to write rotations as k squared, k cubed. These are the rotations. K is the rotation through 90 degrees. So you can think of k rotating the square around here. Let me just draw a picture. You can think of k doing that. And of course, continuing on, it's an element of what we say here, it's an element of order 4, because you apply it 4 times and you get back to the same. Element of order 4. This generates a subgroup of order 4. And then you have the reflection. Well, of course, it's acting as a reflection. And what we have in mind, the group acts. This is the action of K. The group itself is abstract, but it's applied here in the action. This is the action of K. And let's say the action of the reflection goes like that. This is the action of the reflection. This is a really good example because we have seen it motivates many things. Actually, the symmetry group, and let me just, for fun, use color here. The symmetry group has 2 very nice subgroups. The one generated by the rotation and the group of order 2 generated by the reflection, group of order 2. And this is the easiest thing to start out with, which is a semi-direct product. So we talked about it. It's very interesting that we get a very nice semi-direct product. So that's the setup. And G is going to be the symmetry group. Okay? That's one of those things, if I can't understand that, I can't understand anything. You know what I mean? I find an example in life, if I can't understand that, I can't understand anything. So that's great. I start with that. Okay? That's what I do. Quite often my thinking is too complex, and that's my problem. I tend to think in a way that's too complex, and I mean, nobody cares about this example. It's just for fun, but it really gives us a way of thinking. what's going on. Okay. So, now let's see here about these orbits. So I would ask some question, how big are the orbits? G. Remember I was talking, I'm trying to understand, I'm trying to get a good example going of this quotient construction. This is sort of abstract, this equivalence relation. What points, so in other words, what do they look like and so on, which points are equivalent? Well, let me just write here equivalence relation to understand the equivalence relation. How's it look? So let's start experimenting. Now what we can do now, my grandson can do at age 6. So you should just start doing these. I mean, you don't need to be some adult mathematician to start doing what we're going to do. Now we're going to look at the orbits. I mean, like a very small child, what is the orbit of that point? This point here. Let's see what the orbit of that point is. Let's even write it here. Let's call it, I don't know, just for fun, let's call this x1, x2, x3, x4. Okay? And let's call this diagonal is the one we're going to talk about. So g of x1, please tell me what g of x1 is. I know it's early in the morning for some of you. Did you just get up?
No, I was in exam.
You worked all night on the book of Spivak, I know. What's the orbit of x1? I think it's just the 4 other elements, right? It's just the 4 other elements of x1. So, 4 elements of x1. So, let me just start writing down x1, x2. So, I'll write it 1 of x1, k of x1, which is x2, k squared of x1, which is x3, and I don't need to do k fourth because I come back around, that's what it is. That's interesting. I find that interesting. What other points are interesting? Let's take something, you see this point, the key thing here is x1 is fixed by the rotation, by the reflection, by R, right? Reflection fixes x1, it also fixes x3, and x2, x3. Let's see here, therefore we have an interesting idea. What's the, by the way, what's the orbit of x? Let's do some really stupid things. What's the orbit of x3? You don't need to think to do that. Why? I mean, you're smart. Why?
No, sorry.
Don't worry about it. Say anything comes to your mind. What's the orbit of x3?
Still everything? It's still everything? I mean, if you take all the symmetries, or
no, the orbit of the full symmetry group x3. We just saw the full orbit of x1 is these 4 points. Orbit of x3, same. Same. I thought that's why you were laughing. It's the same. It's the same, right? Right? It's this. This is how you do mathematics. You write down something silly, and it looks pretty stupid, really simple. And then you make a little remark, just to clarify everything. If y is in the orbit of x, then g of y equals g of x. That's what Mr. Weiss had in mind when he said it has to be the same thing. Maybe you had it in mind too, right? It's somehow completely clear. You need to check, right? But that's a little remark. So you make it's early in the morning and you made a nice little remark and you're pleased with yourself, that's good. So that's not bad. Now, let's see here, oh, how many points, I'm interested in how many points in this. This orbit has 4 points. Yeah. Well, let's start looking at other points. Let's look at this middle point, which we discussed as crystal's base point. We've called this 0. I always look at things that are so easy that I feel I can really solve them. So what's the orbit of 0? 0. Who said 0? You're right. Yeah, you said 0. Of course, you're right, right? And then you make a remark. If G is acting as a group of linear transformations, which it is in this case, on a vector space, which it is, because it's acting on R2 in this case, then G of the 0 point in that vector space is obviously fixed, because linear transformations fix it. That's what he had in mind, I'm sure. Okay. So discussing a really simple example, we already have some nice information. Now let's see the order of the group. The number of elements in the group is 8. All right? 8, that's why it's called D8. And we make a remark. If G is a finite group, that means a finite order, acting on X, then the number of points in an orbit is at most the number of points in the group. I think that's completely clear, right? Yeah. That's the most you can get. I mean, after all, you're just moving things around with a group, so that's the most you can get. And here we have these, D8. They're not 8 elements here, they're on D8.
You probably also have to take the product of R and the...
Yeah, I forgot the product here, right? I have the product of all these things. So R, yeah. Okay, let me put it R, RK. We know it's semi-direct product, so I have to write it here. R, RK. Well, I always put R on the right. So K, R, K squared, R. This is really terrible. K cubed, R. I'm sorry. I forgot to put these in here. They were here in my head because I wrote the product group, right? Anyway, it's completely clear that, let's see if we can find an orbit of length 8. We found an orbit of length 0, the fixed point, right? Let's see if we can find an orbit of length 8. Here's the square. Here's this reflection, diagonal. And then we have an idea. I'm going to suggest an idea. If X is in, I'm going to express an idea from Italian algebraic. I love Italy and I love Italian geometry. And I'm going to express an idea from at the beginning of Italian geometry, which says, look at general points and try to prove something about what's going on in generally first. And then if you can figure out what's going on generally, you can figure a lot out. So look at general points. If X is in general position, I don't know what that means. And another word I would use here is generic. If F is in some general position, I would hope, we would hope that G of X would be maximal. Special orbits are small. They're special phenomena because something must fix it to make it small. So we would hope that G of X would be as big as possible, would be maximal. Okay, let's give it a shot, just for fun. I don't know, I could just throw the chalk. There it is. Okay. Let's see what happens. I took a point, a random point. That's what you think, a random point. You take a random number generator or something. I don't know how to do that, but I just threw a chalk at it. Okay, let's go through the group. Fortunately, I now wrote it correctly. Where'd it go? Ah, here. Let's go. Well, the identity, okay, that doesn't matter. Now I rotate this point by 90 degrees. So what I'm going to do, rotate, what the double, here, that means I'm rotating around this circle here, right? That's the origin of this thing. And so I put this on a circle. Let's see here. I hope that, I don't know, is that more or less a circle? Is good enough. And let's see here. If that's, okay, that would be an orbit. This would be an orbit. Okay, I got my 4, that's obvious, I'm going to easily get 4 points. Now, my little color coding was not intentional, but a great didactic. It does everything intuition. My intuition told me to color. So, this was the 4 rotations, and then you have the reflection, and all these things times the reflection, everything here. Those are the ones. So reflect, rotate, reflect, rotate, reflect and rotate. So I reflect, and that's good. And now I rotate, reflect, and that's about 90 degrees. And then reflect, wait a minute.
No, we just rotate.
Huh?
We reflect once, we reflect just to rotate.
Can you see what to do here?
Yeah, we reflect already, right?
Oh, we reflect, this was the reflection.
Yeah. Then
Yeah, this was the reflection. From here to here was the reflection.
Yeah.
I get it. So that's just R, basically, R of X. Right?
Yeah.
And now I rotate, that's what you're saying.
Yeah.
R of X, and this is then K R of X. K R of X, right? And now I need to do another rotation. To rotate twice is 180 degrees, so I somehow made a huge mistake in
No, it's fine.
is that fine? Oh yeah, because that would be here more or less, right? So this is K squared R of X. And I do it again, and it has to come out even. No. Why didn't it come out nice? Oh. Well, I see. No, that's right. It's right. And this is K cubed R of X. Right? And then I do K again, I come back to here. Okay. Great. I hope I have 8 points, do I? It should be, right? So if you randomly, that was left-handed, I even missed the thing. But if you randomly hit it and take the point that you hit it, yeah, then the cleaning lady would have to pick it up. So it's okay here. I think we believe it in this case. in this case, that X generic implies G of X has 8 points. And now we come to a very interesting question. At least if I were doing this naively, starting out in, how many points can an orbit have? I can sing it again. How many points does an orbit have? Points can an orbit, this is bad English. This is bad English, I'm sorry. I just put it this way because of the song. What?
I would have another question. For
Yeah.
example, is the set of the set of special points that it is closed, or whether it's closed?
So he's asking a really nice question that I want to ask maybe later on. He's asking, let me reformulate your question. You would hope that generic means this, that if you move it a little bit, it stays generic. Right? That's what that somehow, if it's random and you just move it a little bit, it should stay random. And that means that the way we formulate that in big boys and girls mathematics is the set of generic points is open. And secondly, you believe that most points are generic, and so you say the set of generic points is open and dense. And Mr. Weiss said the non-generic points should be closed maybe. Well, it's just what I just said. No, I think it's better to say the generic points are open and dense, and therefore the complement should be closed and not dense. Yeah, well, maybe it could be, but I don't think so. So, okay.
Sorry, question.
So how many? So I think Mr. Weiss is yes, Mark.
When saying open, what topology are we?
Yes. So this is we're getting ahead of ourselves here, obviously, but in this case, let me speak. He's asking also a very good. Mr. Weiss's question is question 1, yours is question 0. What topology? The square is sitting in the Euclidean plane, right? The operations here that we're dealing with are wonderful. They're much more than continuous. They're even linear. So I think the first topology we want to take is the induced standard topology on the linear on R2. So. Please, if I forget to answer these questions, because they could, actually these questions come after my remark here, right? My remark is just how many points can an orbit have? It's really kind of a simple thing. And of course we've seen a 0. Oh, can we get 2? That's an interesting thing. Can we get? Is there some tiny or small? Oh, we got 0, but is there an orbit with 2 points in it?
We always have at least 1 point, right?
Huh?
How can we have 0 points in an orbit?
Oh, 1 point. All right. He's so nice. I make some stupid remarks. How can we have the 0 points in here? That's really abstract. My grandson informed me on Skype last night that 0 times x is always 0. So that's great. And then he said, however, you can do it the other way. X divided by 0 is always 0, he told me. So I'm fixated on 0. I don't know how to talk to him about x divided by 0. What can you say? So we've seen 1. And we've seen what? Have we seen 4? Yeah, 4, and of course 8. Any other numbers seem possible? I'm asking, what about 2?
It should be possible.
You see a way to get 2. I'm thinking about 2. Oh, no. wait a minute. What are the fixed points of the rotation subgroup? Just the origin, I think. Right? So we can't get to it. Because we always have the rotation at least. Right? So, not possible. Okay. And then we make a remark that even requires a little proof. And some people call this a theorem. You will have to educate me because I've never called this a theorem. Some people call this a theorem. I think some people call this Lagrange theorem. Maybe. This is an example of a triviality that is conceptually maybe important, but it is nevertheless a triviality. And Lagrange is an example of a highly non-trivial, deep-thinking mathematician of the 18th century. So it says this. It says this. You get an I'm going to do a little bit better than Lagrange. I'm going to take an orbit and I'm going to say something very, very important, but what Lagrange's theorem is using is that the orbit can be identified in an absolutely canonical way with G modulo equivalence. So today was a very fun and games. We're not yet finished with fun and games, but we go, maybe I should remark 3 lines. Because this is really important, what I'm about to say. Okay. So this is the fundamental statement and I have to say what this means. This means G modulo the right action of the isotropic group. Please, if you learn anything from me, learn this. Okay, I'm going to explain this to you now. Okay? Now watch. Let's do it, the picture for finite groups. This is true for anything. Groups. Okay, I'm going to leave a big blackboard here to leave. Okay, I'm looking at a finite group action, and I'm saying the orbits all look like this. So let's draw a picture. Here's X, and here is G of X. This orbit goes all over the place. I mean, here's another one, G hat of X, and so on. If you ever get confused, draw the picture. This is a picture in the space G, X. So here's the picture in the space X. Now I'm going to go to the space G. What gets mapped onto X from G, from the action? I think you're saying the right thing. If it gets mapped from G, the action takes X to G of X, right? So that would be the condition that G of X equals X. What gets mapped to X by the action? I'll write it here. What gets mapped to x by g of x, by the g action. Yeah?
Everything in the orbit.
No, what gets, no, what, no, you didn't understand my question. What, you have a g action,
Yes.
okay? So you're looking at the, at the map of g to the orbit. Right? Right. And you go to various points in the orbit, that's the orbit there. What goes to x?
minus 1,
Somebody's saying it right, what?
g minus 1 of x.
Well, let's just see. Do you think g inverse, what do you mean? No, this is like division instead of multiplication. Suppose g of x, what gets mapped to g? What are the g such that g maps x to x?
Identity.
Right? We didn't write it down. As soon as I write it down, it's trivial, right? It's the isotropy group, right? That's the stuff that gets mapped to x. We've turned around the thinking a little bit. Okay? So, but again, this is the question. What are the x, g of x equals x? Okay? So here, I'm up here in g. Here, whatever it is the isotropy group. Okay? Now, what goes, so that's the first question. Second question, I'm writing this down in slang. What gets, this is terrible English, what gets mapped? Don't tell your friends that I write this terrible English on the blackboard, but it's saved in the video, so that's really bad. What gets mapped to g of x on the group? Let's make this really, no, g of x. Okay, so I'm looking at the set of h, you better look at it now, it's the set of h such that what? H of x equals g of x. Right? Set of h such that h of x equals g of x. I claim this is g of x. Why? Or g of g inverse of x. I'm a little worried about inverse here. Let's just see here. If you take the isotropy, it's okay. You take the isotropy, so you write something like this, g h of x, and this is in the isotropy, this is g of x, and if you check it, that's absolutely correct. Okay? So the stuff that gets mapped to g of x is h g of x. No, it's g's of x. That's all the stuff. That means you apply the isotropy first, and then you go over. What gets mapped to g hat of x? Well, you apply the isotropy first, and then you go over. Is it not true? You apply the isotropy first, and then you go. You hit it, you move it. You agree, right? Yes?
How do we know those are the only
I
ones?
can't hear you.
How do we know those are the only ones? Well, where
You
are
can
they?
check it.
Okay.
It's formal. Okay? Yeah. She asks, how do we know they're the only ones? And you just check, you write down a formal thing. Okay, just check. Okay, so that's very interesting. It says that the orbit is equal to g modulo the isotope. Right? Because here's the orbit, here's the isotropy, here's the point, here's the isotropy, here's the point, here's the isotropy. G modulo the isotropy. G modulo the isotropy. Right? Look at that. G modulo the right action of the isotropy. This is the orbit. There is a map from G to the orbit. G of x. And this realizes the orbit as the quotient of G by the right action of the isotropy. What goes to x? The isotropy. What goes to g of x? G times the isotropy. What goes to g hat of x? G hat times the isotropy. It's really silly. Okay. Now, when I was in school, my teacher made a picture which is a box. So here is x, and here is g of x, and here's g hat of x. And now this is the isotropy here. Actually, I'm very happy about my grandson's education. He's learning division, and he's learning division by taking a box and saying if you have so many things in the box and you have so many things horizontally, then you count how many things you have vertically, and that's division, right? If you have 12 things, and he told me last night on Skype, if you have 12 things in this box, and this is 4 and this is 3, then 12 divided by 4 is 3, right? Well, he was telling me, what I wanted to tell you just now, is that the number of points in the orbit, if it's a finite group, if it's not finite, I don't know what to do. If it's number of points in the orbit, is the number of points in the group divided by division is even sometimes divided by the number of points in the isotropy. So that says the isotropy divides the order of the group. This is already a really interesting remark, right? Any action of a finite group, the isotropy has to divide the order of, yeah? It's just counting, and in this case, we don't know what the double that is, but in this case, this is 8, and this is the isotropy group. So the only possible orders, as somebody pointed out how stupid I am, it's possible that the isotropy g of x is 8. It could divide 8. G of x, order. G of x, the isotropy could be 4, but that doesn't happen. But you can check ahead of time. I mean, you just look at the divisors of 8, namely 8, 4, 2, 1. Right? The only possible number of points in the orbit are 8, 4, 2, 1, just by making this little picture of a box, which my grandson told me last night, which is division. Right? This in the books sometimes is called, I think, Lagrange theorem.
Lagrange theorem is for arbitrary subgroups.
You've seen this before. What is it? Is it called Lagrange theorem, or am I wrong?
It's orbit stabilizer, I think we call it. Orbit stabilizer theorem, something like that.
This is, of course, I'm saying something much more complicated, but what, yeah, somewhere around here, Lagrange counted some numbers in the box. Right, but what Martin's saying, right? What Martin is saying is a good way to say it. Orbit stabilizer theorem. You just see that the orbit is really G modulo the right action of the isotropy, and everything else follows from that. And that's a completely general statement. Has nothing to do with finite groups, nothing to do with anything. It's very useful, right? I mean, it's just, right? And I was a little bit quick here, but you can easily, this is what Maria's pointing out, you really just, it's a formal thing to check what I just said. What goes to G of X is simply, yeah, the right thing of that. So I'm happy that we all see this. I'm going to make a pause to give us a little break, so we're not so tired. I don't want to destroy you, but not right now, not yet a little pause. Well, you'll tell me, we'll see. This morning, maybe we don't need a pause. Okay. So let's go back to the square. One of the reasons I love teaching mathematics is it forces me to rethink in elementary terms, you know, what I think I understand and maybe I haven't quite understood. So I'm going to go back to the square, and now x is the square, and G is the dihedral group. And I want to understand what does it, so after seeing this, I asked the most brutal question of all. What describe x modulo G? Now I may get to some of these questions about the topology and open sets and all of that, right? But I realized last time, Prof was telling me, when you first see this stuff, it makes you crazy. Pravat survived. He looks like a nice guy. He's not completely crazy. But, yeah. But I won't say so much about topology. First, let's just do some odd thinking. Okay? And let's take a picture of the square. And what I'm going to do, I'm going to talk about a thing that is absolutely fundamental. It will come up in all your lives, and no matter what subject you're in. It doesn't matter. And so it's fundamental. And since it's so fundamental, we're going to be talking about something called fundamental region. Okay? That's just a word now. Okay? So this is going to be a fundamental region in the square. Now, I'm going to motivate this by something you all know about, at least I'm sure you know about, fractions. I love saying it like that. It reminds me of a wonderful mathematician who sings at the piano. Do you know Tom Lehrer? The last name I spoke, he's an American who wrote really funny, cynical songs. For example, all of you are young, but I will tell you about my generation. You would perhaps find this amusing. Of course, I was absolutely against any form of violence in war, as you might guess. I'm very much against it. And one of the big things in the United States was the danger of communism. So I think you said you were from Eastern Europe.
No.
I thought you were from Eastern Europe.
No, Central Asia.
Huh?
Central Asia.
Central Asia, yes, but that was the Soviet Union, excuse me.
That's true.
That's very good. Okay. Now, when you're so young, you were born in Uzbekistan, right?
Yeah.
Really, it was never part of. When you were born, it was not part of the Soviet Union.
No, it was.
You're lucky. So, from the point of, so there was this blanket, it's hard for you to understand, there was this blanket fear in the United States of communism. Communism. Nobody knew what it meant. Nobody had ever heard of Lenin, maybe, or maybe Lenin, maybe not, but Marx certainly not. Yes, so there was, and Tom Lehrer wrote all of these things about new math, so he wrote all these cynical remarks about new math. Look at Lehrer, Tom Lehrer. Play some of his songs on, they're really funny. And one of the lines, is, he's going off to war. He's an anti-war guy. And he's telling his mommy, his mother, he's going back, he's going to war. And the line in the song is, "So long, mommy, I'm gonna kill a commie." It's just incredible, incredibly silly. Yes. So I like him very much, and I think one of his songs is New Math, isn't it? And the New Math thing is really funny. So, and I think, I'm not sure, he may have sung a song about fractions, something like this. But as you know, 1/2 and 2/4 and 3/6, I'm putting this in some stupid order, and minus 1/2, and so on, is the equivalence class. That is a set of representatives of a rational number. All these numbers are the same because you're modding out by equivalence, right? Everybody here in this room knows this. This is right. Frederick told me that last night on Skype. All these things are the same. And what you do in life, your mother and your father and your sister and brother will not even bother with this stuff. They will say it's 1/2. Isn't that true? I think if you write it as a right? Isn't it true, mate? Yeah? You say no, it's not true.
Well, you wrote -1/2.
Oh, I wrote minus 1/2. Oh, sorry, I forgot a minus sign. Yeah, thank you. Yeah, he's always right. So, yeah. So you take a representative of the equivalence class, and you like it. There's a way of taking it. It's the two numbers are relatively prime, right? And positive, for example. That's your point, actually. Take both numbers, positive and relatively prime, of this. Yeah, okay. And then you get one. So we're going to try to do it here. And the word that we're going to use here is find a slice. So you have to have a feeling. By the way, I was just in Hamburg. Is anybody here from Hamburg? You know, the German people know Hamburg, certainly. It's a wonderful city. There's a wonderful exhibition of a great artist named Barlach. Maybe you've heard of this wonderful German artist from northern Germany. Grew up in northern Germany. He was also completely anti-violence. You look at his work oriented toward protesting the First World War and around the First World War. It was absolutely amazing. And some of his sculptures, he has a something like, is anybody here from? Oh, maybe you're from Kenya, right? So you might go into the jungle in Kenya and cut things down with things. I don't know, you call it a machete or something like this. So Balak had these people. This was very symbolic, not of Kenya, but of some sort of violent motion with this thing like this, or so it's incredible. So you maybe think of making a slice, and the reason I'm telling you this is if you have up here what Barlach might have done to express some terrible thing, you have your orbits or your equivalence classes up here. Here's x modulo g, and here's x. And it's a terrible thing here. You have the equivalence class of all these things, say 1/2, but all these terrible things in it. And what you do is you take the representative up here, 1/2, which is exactly one point in the equivalence class. And what you do is you cut across every equivalence class. Ah! Yes, so you just pretend that you're someplace in Africa in some terrible jungle where you have to cut. Oh, a great place is maybe Japan, because they have wonderful bamboo. Do you know how wonderful bamboo is? And you go in these, I don't know if you've seen these Japanese bamboo things, it's just incredible. I don't know other countries too, but I've seen them in Japan. Wonderful forests of bamboo, right? And that's a perfect example. Sorry, Kenya is no longer an example. So, in Japan, you go into a bamboo forest. You can see this on the web in beautiful pictures. And there are just all these things like this everywhere, dancing thing. And just think of, if you were powerful enough, I used to play golf, so you're powerful enough to just cut across each thing and take a representative of each bamboo, okay? Of each bamboo tree. One, not a little disc, I mean one. Okay? So this is slice. And let's use sigma for the word slice, just to remind us of the word slice. Okay. So for 1/2, we just, everybody here knows the slice for the fractions. And now the question is here. You've done it all your life. My grandson has done it in age 6. And I'm telling you to do it again for the dihedral group's action on the square. Right? It's the same thing, right? Every orbit, take 1 point, right? Now, you don't want it in some random way. I'll take that one for that orbit, that one for that orbit, that one for that orbit. I mean, that's stupid. You get no feeling because what you're trying to do is get a feeling for the quotient. Isn't it true? You know, I take 1/2 for that orbit, and then it's for this other thing, I'll take 3, I'll take, I don't know, 15, 30, no, that's already taken 1/2, I'll take 90, no, that's already, so let's take 11, no, that's 11 times 4, 11/44 for that one, right? Or so I'll just take some random choice for all these different fractions, that would be stupid, right? You want to have a system for it. And that means you want to have a geometric representation of the quotient upstairs as a slice. You see what I'm saying? That looks good, that reflects what the structure of the quotient is. Right? Okay. So you want to find a region F with 2 properties, which may not be possible, but I'll try, such that for all x, oh no, just 1 property, such that for all x, the orbit g of x intersects f for fundamental, in 1 point, in exactly 1 point. I wrote this in words to emphasize it. Every orbit hits it exactly 1 point. That's what I told you. Take the machete and cut across the bamboo jungle and intersect each tree in exactly 1 point. Right? And then you're getting some sort of picture of the quotient. Right? You don't have any bamboo in Egypt.
We have.
You do? Do you eat bamboo? I love to eat bamboo. Oh, really? Is it?
Yeah, and it's pretty cheap.
You like to eat bamboo?
Yeah.
I love it too.
But my teeth don't like it.
Y'all, do you know the bamboo is a wonderful thing to eat? Okay, I'm so happy you have bamboo in Egypt. Do you have sushi in it? I love sushi. Do you like sushi? No, no. Vietnam, you probably have a lot of raw fish that you eat, right? Or not? Fish, of course, but raw fish?
Yes, but I don't eat.
He doesn't eat it. It's too dangerous. And, okay. So, that's what you want. And now I'm going to suggest an idea here. An experiment here. I'm going to put the diagonal back here. And I'm going to see if, just for fun, I'm going to start up here. I'm going to start up in this quadrant here and see what points I can get. So, does everybody agree that if I start up here, I start here, for example, in this, if I start here with a point, I can get everything here, right? So I can get everything here, right? And if I reflect, wait a minute, no, it's even better. What, no, is that right? Is that what I get? No.
You get everything.
What do I get if I reflect along here?
Oh, that part.
Is that exactly what I get? Yes, because I'm just reflecting around this square, right? And now if I rotate this by 90 degrees, I get this, right? Right? And now if I rotate this by 90 degrees, what do I get? Am I doing this right? First I reflect to get this, and then I start rotating. Is this correct, the rotation of that?
Well, it really depends on what you rotate. If you reflect and rotate, you get the lower right.
So I'm first going to, what I'm looking at is I reflect, and then I start rotating. Reflect, and then rotate, and then rotate again. I want to know what I get if I do this. Can you see it better than I am?
The triangle on the bottom.
Can you see it, Mr. Fan?
Lower track on the right.
Do I also get the, what do I get? Can you draw? Maybe we shade it in, yes.
First you rotate this to this.
Yeah, reflect.
Reflect this to this.
Yes, and now start rotating.
So this side become this side,
Yeah.
this side, and this side. So you get this.
Is that all I get? Can I rotate some more?
You can rotate this to get this.
So I reflect this to this, right? And then I rotate, I get that.
You rotate this to get this.
Oh. Oh, he's rotating and reflecting.
You know, like if you rotate first and you get like this,
Do I get all of that?
you get these.
He sees it immediately, yeah.
And then you only rotate this without reflecting, you get the other one. This.
So we get it all.
And you get all of it.
So, okay, Mr. Pham convinced me, I don't know if everybody else is convinced, at least Mr. Pham is convinced, that if you, maybe I should use color. Maybe green. So, dedicated to Greta Thunberg again with, because she's fundamental. We start with that. Okay, that's where I start. You agree? That's where we started. And Mr. Pham rotated everything around. You got everything, right?
But then I would also have,
Somebody else. You see it,
do you only do the,
Tristan? I've got it now.
yeah,
Right?
do you only do the actions which you have noted down there? Or,
No, I don't think so. I think he was very fast.
yeah, because then you also have to add K,
Yeah,
K,
you have to use everything.
yeah.
It's good. I think it's what he said. I can't just get away with these elements of order 4 or more or less order 4. I really need all 8 because we know that the group has order 8 and the generic orbit has 8 points in it. So, right. So, which Tristan's. I'm working to memorize your name. Is it the same as the Wagner opera? Tristan and Isolde.
Yes.
So very classical. So it's a very nice name in German, well, philosophy and music. So, Mr. Pham was very quick, I'm not so quick, but yeah, I think you're absolutely right. If you start here with this upper little wedge, you get everything. Yeah? And now now is the part, let's hope that the upper wedge, I'm going to do it in green, wedge. This is a wedge. Here. This is the wedge. This, we hope this equals a fundamental region. Now let's check it. I've got to check, and I think that's what he's just saying. You start in that wedge, and you get everything by applying the group. That's what you believe, right? I think it's true. By the way, what is the wedge for you? The thing with boundary or not with boundary? It's a question. I would like to first think the thing with boundary. Okay? So let me put this thing in here with boundary. Okay, wedge with boundary. Now, let's believe Mr. Pham, I believe you also, we get everything. We're safe if we put in boundary. Now, is that really a fundamental region? I'm interested.
Maybe you can intersect twice in the boundary.
He's worried about the boundary.
I mean, you only allowed to intersect at one point.
You're only allowed to intersect, he's louder, I can hear him now. So he says you're only allowed to intersect in one point, right? And isn't it true that if you take that was more or less my random thing. If you take something in here, its orbit, it goes completely outside. I think you get a feeling for that. But isn't there a transformation? You could take something here, and it could map it over to here. That's what Mr. Pham's worried about. What is the transformation? It starts here and maybe goes to here. I don't know. I mean, can you tell me what it is, somebody?
I mean, it's not possible.
That's not possible?
Because it's an angle of 45 degrees, and we can only get angles of 90 degrees.
I cannot map some point on the boundary here to over here. Are you sure?
Yeah.
Really? I don't know. I mean, what happened? No. It has to be, Nicholas, because look, I don't know what Mr. Pham did, but he went over here and went over here and went over here and so on, and finally he got up to here, right?
But not that side.
It would end up on the other side.
Yeah. So he got around to here. So
But he maps the same point to the same point if you go the full circle. I mean,
no, he didn't go to the whole. Yeah, of course, if you go to the full. But in order to get to here, in order to pick up this wedge, he had to map this big thing onto that, right? That means the boundary had to go into the boundary. That means some of these boundaries, something got identified with that boundary pool.
But the intersection is still only one point, right?
No, I'm saying something on this boundary had to be identified with that boundary.
We had to reflect around the middle axis to get there, so basically what we're getting is that side, not the slanted side, but the vertical side.
What are you saying, Papa? Can you explain it on the blackboard? I hope you see this is really interesting, right? To get this example. It's a tricky example, but it's nice.
And for this, from here to here to get to here, we have to first reflect once and then rotate it 4 times. So what we get is this will be mapped to this side. So
What will be mapped to that side?
this side from this triangle will be mapped to this side from this side triangle. So there is no identification between this and this.
So this thing, what you're telling me is the elements that we applied fix this point was.
Yeah, if we map this triangle on this one.
So, really?
Yeah.
So,
Also because we have to go.
oh, I guess that's what Mr. Weiss is also saying. that-
More or less that amounts to reflection along this axis.
So the end result is effectively reflection around that axis.
Yeah.
I see. So, okay. So that's great. So what you're saying is that in fact this is fixed points.
Yeah, that map.
Well, I don't care about the map. I mean, right? So let's check this out. So let's go here to yeah. I understand what you just said. So this is fixed. This is fixed points, and I make this wedge. So here g of x equals x. Okay, what about here, everybody? What the orbit here? What's the orbit of something on the diagonal? It must be 4 points. Yeah.
I think we make, there can't be fixed points. Remember we said the rotation group has no fixed points outside of 0. So
That's
the
right.
points on the boundary there are coming from the lower triangle, not this line, so they're not fixed points.
Okay, what do you say? Well, can you come up and draw this much? It's pretty interesting, actually. I'm not sure, Robert, I'm not sure you're right. I think Martin's going to disagree with you. I'm not sure.
We had this as a fundamental
Yeah.
region, and then we reflected this. So
Yeah.
we got a square. And then we can now rotate that.
Oh, good way of thinking.
360.
We get everything.
Yeah.
Yeah.
So that at this point was mapped here, and that's what then comes back after 3 rotations, not 4.
Yeah, but that's what, I think that's what Prabhat said. This point was first mapped here, and now you rotate here.
By a reflection, not a rotation, yes. This was reflection, and then we got 3 rotations back.
Yes.
So the element actually is K3 now, not K4.
Yes.
This is what
Okay, tell me where this point goes.
first is reflected here,
Yeah.
and then
Rotate.
rotated 3 times. Once here, once here, finally there.
And it's really fixed.
Yes, after the 4th.
Yeah, but that's what Prabhat is saying. You're absolutely,
Yeah.
you're absolutely right.
But not fixed by the rotation group, by the entire.
No. Oh, I see. No. What I was writing down is stupid. It's not fixed. It's somehow fixed, but it's procedure. So what's the orbit of a point there?
Which point?
Oh, well, we know it's stupid. An orbit of a point here. Yes, an orbit of a point here. That's what I asked you. It's just these 4 points. Right?
Yeah.
That's what you agree.
Yes.
Okay, great. So I misunderstood what Prabhupada was saying. This is clarified now by Martin. That orbit, there are 4 points in that, just the rotation. Right? And what are the points? What about these points? How many are in that?
Also 4.
Huh?
4.
Also 4?
But in the former one, it's 8.
I kind of hope that it's 1, 2, 3, 4, 5, 6, 7, 8. I'm not sure.
It's only if you take something which is not on the boundary. Or, I mean, not on those, not on the vertical, not on the diagonal.
Yes, so these are, oh, okay, so this is a special point, this is fixed, and this is a special point, it is fixed by the reflection, and then rotated around. So, this has 4 points. This point,
This is arbitrary. That's a generic.
that's generic? Is that generic? Yeah, 1, 2, 3, 4, 5, 6, 7, 8. It's generic, right? So this point is 8. and this point, what did we say, certainly the reflection, oh, well, the reflection fixes it and rotation rotates it, so that's 4 again. Okay. And in here is also 8. Okay. Okay. It's sort of fun to do it, at least I have fun doing it, right? It's understanding, we're understanding the quotient. Everybody agrees here, the quotient is effectively this wedge, right? Because we picked every, right? The quotient is this wedge. So, all right? So let's go. I think we can just lecture 2 hours, and because we have so much fun, we can finish and go to lunch. We don't have to have a break. You don't need a break because you came late.
Yeah, but I was in exam, so it's like 4 hours straight.
You were where?
In exam. Exam.
Oh, you were in the exam?
Yeah,
Why were you taking the exam?
because I didn't went to the regular.
Yeah, okay. This is really interesting. So, x is a square. G is the dihedral group. We look at the picture x. We look at x modulo G. In this case, the orbits are finite. In fact, let's have some fun. Let's do Mr. Weiss's exercise. What?
So I wonder, now in this case, the topology on this fundamental region is the same topology as on the square. But is this not the same for every fundamental region? Because we could also scatter parts all over the square to make a fundamental region.
So, Mr. Weiss asked, we made our favorite one here.
Yeah.
You're asking if every fundamental region somehow
It's the
is the
topology.
same.
Yeah.
Don't you believe it?
I don't know, I'm not fully convinced. Maybe there's a way to create a fundamental region just out of many lines.
Take fundamental, do you understand what he's asking? Take two fundamental regions. We could have taken something else completely crazy, maybe. Yeah, take two of them. And how do they compare? I mean, they are versions of the quotient in some sense, so that's good. And now each one represents one orbit. So if I'm in this fundamental region, there's exactly one transformation. I have x here. There's exactly one transformation that maps x to this other point. So, okay, now I move x. Yes, you see what I'm saying? I move x to y, and then there's exactly one that goes over, right? The trouble is, when you move x to y, you might change the guy that moved it over, right? Now you have to check that when, at least locally, when you see what I'm saying? When under small movements of x to y, this element that moves from one to the other fundamental region is unique. And then you pave out your two fundamental regions by this kind of argument, and I think you've come very close to showing unicity.
Oh, okay.
You just think about it in this way, is the way I would think about it, yeah? It's an interesting, you understand what, that's an interesting question for writing a little paper about this course, right? I mean, his question is very good, right? I mean, some guy, your teacher picks out some fundamental region and says, this is it, guys. I mean, that's ridiculous, right? Because any fundamental region should give you a picture of the base, of the quotient, right? So, what I want to do is talk about, I think it was Mr. Weiss's question and Martin's question, everybody's question in some sense. Okay, here's this orbit of 8 points. Oh, what I'm going to do is call this, I'm going to call this A in here. I'm going to call this B up in here. I'm going to call this C here. I'm going to call this D here. And oh, this is the same as B, right? No. How is it possible? I must have made a mistake here.
I mean, A and B are kind of the same.
Yeah, but what about this guy here?
It's the same as D.
It's the same, right?
Yeah.
Why did I write 4 here?
Should be A.
By
No,
mistake.
it's also 4.
Huh?
Right, that's it.
No, it's also 8, right?
No, it also has 4. Because if you
Well,
if
is
you-
this point and this point the same?
no, because if you rotate and reflect, you get back to the same.
Oh, yeah. So this point's really different. A, B, C, D. Okay, E.
So you just need 4 points.
I only need 4 points.
Yeah, basically D, or even less, maybe 3.
A, B, C, D.
Maybe
Yeah.
A and B are more or less the same.
A and B are more or less the same. Yes. So I will not take, I don't know.
And C and D are also the same.
You say C, oh, what you're saying is these points are somehow the same phenomenon. Oh, great. So Mr. Weiss claims, and I think he's probably right. I call this A, what do you want to call, and I don't have to call this anything. I call this B, and I call this C. So from the qualitative point of view, I only have 3 types of points. Okay, so here is general. And general. And here is less general. And that's it, right? And very special. Okay? Isn't that what you're saying? Right. Okay. Now, mathematics is never rigid. Move your points. Move. It stays. This answers, in some sense, your question. If I move my points in an open set, they stay the same. But I go to non-generic points, and when you move over here, you will see that these points move over here and become fixed points. They move over here and become, not fixed points, but less general. How in the devil did I didn't write 8 points. 1, 2, 4, 6, 8. Yeah? So they come over here and degenerate, not completely degenerate, and they come over here, I'm moving them to a 4-point orbit. You understand, if I'm moving over here, say for example to the diagonal, I move here. The orbit, when I get here, the orbit is 4, but everything here is 8. And when I move completely down here, everything is 0. Only 1 point. Oh, it's up here, the point is up here. So that's a picture of, what is going on with the orbits. Generic it is, there are 8 points. You start moving and they degenerate into 4-point orbits. Right? And the complete degeneration is into a fixed point. Now there may be 2 types of 4-point orbits, I'm not sure. Is this 4 point, are all these orbits more or less the same quality or not? Yeah? Or the isotropic groups are more or less the same, I think. Okay, I think this is true. Okay, that's an analysis, and now the picture you get, x modulo g, is the picture of that is the wedge. It's really, oh dear, I lost my green. Oh, there it is over here. I really like Miss Thunberg, what she's trying to do. So I try to dedicate as much as possible. This is the wedge, created basically by Mr. Pham. And the wedge we've decided is closed, including all boundary points, right? So it's a closed wedge. Wedge is a fundamental region. That means this quotient looks like that. You agree? Good. Now, do you like that? I mean, does this, tell me about this. Upstairs I have some, yeah, is it of the same class? You said structure preserving in the last lecture. Is it more or less of the same type, same thing as upstairs in terms of structure? Would you agree? Tristan, you're worried about this.
I haven't made up my mind.
Okay, say anything to me about the structure upstairs before we've made the quote. Anything to me. What's it like?
House of,
Hmm?
house of
Okay, you're right. It has, in general sense, it's a perfect, almost a map.
completely house of.
Yeah, I don't know. It's a wonderful topology and all this stuff. But I'm look at the geometry of it. If you would say, I mean, this is not these. Here's the square, and here's the square, and here's the quotient. Do they have anything? What would you say they have in common? Marty, what would you say? I mean,
what terms? Geometrically or?
yeah, just say something what they look like. I mean, if I were, nobody here is blind, but I have some friends who are blind, and explain. Okay, I close my eyes. Explain to me about both of those things. The geometric structure. Tell me about the geometric structure, Mark. I mean, don't say it's a square, but say you know some structural phenomena. Okay, hey, let me ask you. Well, Mr. Weiss.
I mean, the fundamental or the axis decomposable into the fundamental regions or multiples of the fundamental region.
Well, that's almost a tautology, right? Because because that's how we define the fundamental region. That's good. That's good, of course. Okay. How would you define the square? If some blind guy came into the room, my friend in Moscow, he passed away, but a wonderful mathematician, Toya Vitushkin. He's been blind since the age of 14, which is a big advantage. If you're blinded at age 14, you still have some ideas about many things. But he was older than I am, and he was playing as a kid with a bomb from World War II, and it blew up in his face. Yeah, it's a terrible thing. So Vitushkin is a great mathematician. Well, he's passed away, hasn't he? And I talked to Toya. It's very, very interesting to talk to a blind person. Yeah? And I explain what I'm seeing because I'm drawing my pictures on the board. And Toya is in his, Anatol is his name, but Toya is the short version of Anatol in Russian. You know.
Yeah.
Toya, I say, Toya. He says, He's always saying, just, Alan, explain what you're talking about. And of course, I have this picture here on the board, what I'm talking about. Of course, it's in some other, I'm talking about a complex analysis. Yeah. Yeah. Deepak, I mean, how are you going to explain these pictures to a blind guy?
Well, that looks like a triangle.
He doesn't know what a triangle is. I mean, say this is something, no, okay, a blind kid, say. I mean, he doesn't know what, he knows a little bit of mathematics. So it's in the plane. I'll start out, I'll give you, we start out, we have a figure, a shape, which is a set in the plane. Okay.
Then take three different points and then connect them. Well, take three different points, the connect them. So I'm describing a triangle.
Okay, he wants to decide, is a triangle,
Well, it's a triangle.
okay, you want to say, that's what Mr. Weiss was saying, that this is a union of triangles. It's actually true, right? That's what he was saying. A union of fundamental regions is somehow a union of triangles, right? Yeah. I think a triangle is too fine of the structure. How do you define a triangle in structure? I mean, not so fine. I mean, for example, Vitushkin would say, Alan, I mean, he can draw, he can draw. He'd say, Alan, he doesn't draw very well. He would say, is this a triangle? Is this the kind of figure?
Well, you could say it's maybe a convex solid or a convex polytope of 3.
Okay, maybe he knows what is a polygon. Or
Exactly, it's a polygon.
maybe he knows what a polygon is. Isn't that a really fine structure? I mean, could you hope that if you start with the thing that's a polygon and you have an action of a finite group, you get a quotient which is a polygon? I mean, that's really fine, right? Right? Isn't that refined? How would you define a square in the plane, not in some fine way like a triangle? I mean, with mathematical operations. I will give you one operation, is called equality, and I will give you another operation, which is called inequality. And I will allow you to describe these figures in the plane using equality or inequality. I mean, don't you think you could do it? Well, first of all, I would say convex is a good thing, right? That's pretty fine. Isn't a square defined by inequalities? Linear inequalities? Isn't a triangle defined by linear inequalities? Isn't it true? Isn't that an interesting way to define a set? By inequalities, right? In all of your mathematical training, you have been propagandized, like Americans are propagandized in the time of I was growing up, to go on, mommy, I'm going to kill a commie. You've been propagandized to think in terms of equalities, whereas a fundamental thing to write down is an inequality. Right? A square cannot be defined by equalities, trivially by inequalities. The quotient cannot be defined by equalities, but trivially inequalities. But maybe you want some equalities and some inequalities. Let me just say, if you're interested, this is the subject of real algebraic geometry. You have an object over the reals defined. It is defined by equalities or inequalities. Yes. You have a finite group action on this object which is defined by equalities or inequalities over the reals. And the quotient is of the same type. Okay. That's a megasatz. What?
These are
Can you be louder?
These are semi-algebraic sets. What topology is usually placed on?
Okay, so he's asking which topology and so on. I'm even neglecting to discuss topology. Let us consider the action of a finite group. First of all, finite group of algebraic transformations, let's say linear transformations. Okay? Finite group of linear transformations. Start. On Rn. Basic set. Real algebraic set is defined by equalities or inequalities. That is the subject of real algebraic geometry. Equalities or inequalities. Everything you write down is defined by inequalities or equalities, really. Right? It's not unrelated to computer science. I mean, you're only limited in certain operations. It's very close to logic. Yeah? Very close to logic. You have certain operations that are allowed, equalities, inequalities, certain equations, finite group action, thing defined by inequalities or equalities, quotient can be realized as being defined by equalities or inequalities. Very interesting. I'm not making that precise at all. Obviously, I don't want to here. But I hope, I don't want to bother Tristan. It's boring, right? But this is what you're talking about. You have structure upstairs, structure downstairs, and you want, that's fine structure. He said triangle's too fine, right? You want something that's some degree of generality, right? Structure upstairs, well, topology is very weak. Open sets, and so that's what we were talking about before, open sets and so on. Here it's completely clear, we have the induced topology. Here you have just the quotient topology, everything's okay. But the beautiful thing is, upstairs is defined by equalities and inequalities, downstairs is defined by equalities. Pretty good, huh? It's not just some arbitrary set. Okay. You stay inside some context. Okay, so that was, and now, of course, when you were in school, and I want to do this on Skype with Frederick, when I have a chance, it's the standard thing we've done in school. We take a rectangle, and we take the group C2, and the one C2 is this group, and the other C2 is this group, right? You did this in school, right? And you say that the quotient is this thing, right? Everybody here did this in school, huh? Or no? You didn't do this in school. You take this and you do this and you take this and you do this. You didn't do that? You didn't make a torus in school? Well, please go home and make a torus. Okay. It's very interesting. You can see visually that it's going to be a torus, right? But it says that the torus itself has real algebraic structure. It looks analytic, but it has real algebraic structure because it's a quotient of a real algebraic object by a real algebraic group. Right? Okay. And this is I have used that theorem many, many times in my life. Don't neglect it. Right? Don't neglect the structure that is there. Okay, see you this afternoon at 4 o'clock.